think that would be it. Yeah, so everyone was able to reach the web page? Nope. Okay, I will leave it for a little bit longer.
You can still contact Vladimir and just scan it from his notebook afterwards. So I think I can.
I'm doing it the old-fashioned way.
I got the second one. Can I ask the first presenter, Felix? You come with your notebook or?
Yep.
I got the second
your
one.
notebook for here?
No.
Okay, since right now the 9:25, so we are a little 10 minutes behind.
Yeah, but we're going to skip. Skip a bit of
Okay, welcome everybody. This is Joseph Kyeong. This is my first participation of this OMNeT related meeting since 2015. I've just worked and lived in the UK 7 years and then moved to China, so that's why I just missed this nice opportunity of the OMNeT Community Summit. By the way, we are a little bit behind the schedule, so 10 minutes behind. So program table, the first presentations will start from 9:15, but we already 9:25, so we will make some changes accordingly, so 9:25. So our first speaker is Felix, Weinrank, Irene, I'm just trying to my best, Rüngeler, Michael, Tüxen, and Erwin, Rathgeb from Germany. The title is SCTP User Message Interleaving Integration and Validation. So the presenters will introduce by themselves, and maybe I think that's.
What have you done?
I've done nothing.
It was working.
Yeah, it was.
Okay, so I need to be here so
Okay. Oh. Okay.
So general format is
the
that. The
HDMI.
long presentation is maybe
Yeah.
25, short is 20. At the end of the presentation, 5 minutes are dedicated for question and answer session. So I'll give you some sign before, maybe 5 minutes before the presentation, okay? Just kind of notice. Okay, maybe let's get started.
Okay.
Could you please introduce yourself?
Yeah. My name is Felix Weinrank. I'm from the University of Applied Sciences in Münster, and we focus on network programming. So we're a network programming lab, and I would like to introduce the user message interleaving, especially integration and validation into the OMNeT INET model. And I will start with a short outline, introduction to SCTP, what is message interleaving and what are stream schedulers, how we integrated them, how we validated our integration measurement results, and a short outlook. So SCTP is Stream Control Transmission Protocol. It's a layer 4 protocol like TCP or UDP, and it's message oriented and multi-home. So it's about 16 years old. They started in the early 2000s. And it's originally designed for small messages, signaling messages in the mobile networks. And currently it's also used for WebRTC. But this is a newer topic where the WebRTC data channels are driven by SCTP. And we see here between two peers, we have an association with several streams. This will be important, especially the streams in the future slides. So, what is interleaving? We have a sender-side head-of-line blocking sometimes. What does it mean? When I have two or more streams to a peer, and I send a very large message on one stream, I block all other streams. So, for example, I send a DVD to them, and I send small chat messages on another stream. The small chat messages are blocked. So this is sender-side head-of-line blocking, and message interleaving reduces this head-of-line blocking to this is done by making it possible that small messages can interleave big messages. Big messages are stopped, or chunked and stopped, and small messages can be sent. And this is specified by an ITF draft. It's ongoing work. The URL is there in the bottom left side. And this is a picture how data transfer on 3 streams is done with non-interleaving. So we see on the left side stream null, there are 2 large messages queued. In stream 1, there are small messages queued, and in stream 2, and the green one, there are bigger, medium-sized messages. And what's happening is the stream scheduler chooses a stream. In this particular case, the stream null, and all messages. The message is chunked. This is the maximum transmission unit, which can be sent at 1 message to over the network. And the big messages are chunked, and the stream scheduler is locked on stream 1. So we have to wait until the complete blue message has been transferred, and only after that I can send from the next stream, and this continues. And this is head-of-line blocking. Imagine we don't have here only 4 messages. We have, for example, thousands or a gigabyte, which we want to send, and so we can send any small messages like chat. And by interleaving, with interleaving, we can send all these small chunks independently of the original message size. So the chunks are transferred. The only criteria for the stream scheduler is the priority and not the stream scheduler is not locked on stream. So our integration to the OMNeT INET simulation model follows the IETF draft, and it's only controlled by a single parameter. It's the iData parameter, which that chooses if iData support is activated or not. And the interleaving support is announced by the peers in the 4-way handshake of SCTP, and if both peers announce interleaving support, interleaving is used. So only a single parameter. And how we validated our extension, this is focus of this presentation. First, Wireshark. Wireshark is a great tool to do packet inspection with the OMNeT INET models when it comes to weird behavior or to check if all the headers are correctly. So we were able to generate a Wireshark pcap-ng file and analyze our new extension within Wireshark. And Wireshark also has support for the iData extension of SCTP. The next tool we used is Packetflow. Packetflow has been introduced last year by Michael Tüxen here. And Packetflow is a script-based testing tool for transport protocols, originally developed by Google. And we extended Packetflow by support for SCTP. And currently we have over 120 tests for interleaving specific tests. And we can use the same tests for OMNeT, OMNeT INET, and for FreeBSD. Packetflow has been originally developed for Linux and then been ported to FreeBSD. And now it's also available in OMNeT, and we run the same tests. And external interface test. OMNeT INET has an external interface where we are able to, I got the phrase hardware in the loop. I'm not sure if this is right, but we can communicate with the real network. So testing against the FreeBSD stack, which also has the iData extension implemented, and this was very, very helpful. And small measurement scenario, we have here an SCTP client, SCTP server, and a client server where we generate random UDP background traffic. And the architecture of our measurement is we have a standard host on the left side with 2 traffic generators. The traffic generators represent, each generator represents a stream. For example, stream 1 is a saturated stream with large messages and a low priority. This is, for example, in file transfer. And stream 2 is not saturated, has small messages like chats, and has a high priority. And this is the path the data goes. And on the right side, we have the chart where we show the link delay. So the blue one is the delay increases with the message size of the stream with the large messages. So we have on stream 1 large messages, and when we increase the message size, the small messages with high priority takes more and more time to be transferred. This is blue line theory. The gray line is our measurement, and we see that if we use interleaving, the delay stays at this constant level. And this is because on the left side we have the formulas we use to generate the theoretical chart. We see on the top formula that there's S message is the message size plus how many headers we have to add, because when we fragment a message into 10 pieces, we have the message size plus 10 times the header. And additional link delay and buffer delay. And this formula on the bottom shows, okay, with message interleaving, our delay is half of the message transmission maximum transmission unit, and added to the link buffer and the delay, the link delay and buffer delay. So, small conclusion. Message interleaving reduces head-of-line blocking. So this is not new, but we can show it in the simulation. And we were very happy that we are able to use Wireshark, Packetflow, and the external interface to validate our extension. This helped a lot because simulating something to the blue and do not know what's happening and if this is correct what I'm doing, there it's very helpful to have these tools. And in Outlook, we have to do buffer improvements because this extension has shown that when we use interleaving, we have to take care of buffers because sometimes there's a lock that we lock our buffers when we start interleaving. And we will introduce new stream schedulers to the SCTP model. For example, weighted fair queuing, which is the stream scheduler which is used for WebRTC data channels. And we will add this to the SCTP simulation model. Thank you.
Okay, let's give first clap. Perfect timing, so we can have up to 10 minutes for question and answer sessions. So please ask what other questions you have to try this advanced presentation.
Well, can you tell me a little bit more about the Packetflow? I remember just a few ideas from the last year presentation about it. Like, what is the procedure when you are using the test to verify that the protocol is behaving or misbehaving?
Thinking about to start the presentation from the last year. I will. So this is a small example of a Packetflow test script. Packetflow is presentation blue. Packetflow allows you to inject packets, and it checks the response. And this it's like an automated test tool for TCP, UDP, and currently SCTP. And
and this is the code of the packet tree, like what I'm looking at.
Yep.
Yeah. So you can kind of script the behavior of messages and
Yep.
write some conditions.
Yep. I think it's in the OMNeT INET. Come on. So, for example, this is a packet drill script which tests the INET retransmissions of SCTP. And there are tests for SCTP, TCP, and UDP. Batteries included.
So done with your question?
Yeah, okay. I will check it. No,
Yep.
Yes, it's more detailed.
just a teaser.
More detailed discussions you can be outside of the room during the coffee break. So, but we still can have maybe one or two questions because the 5 minutes remaining. Yes.
So, on a specific question about the use of the iData to cancel out the line walking.
Yep.
Then once again, why you think that the iData solves your problems of that line walking? Why specifically iData instead of the normal?
And we have a look at this slide. iData solved the problem that the fragments of a large user message have to have consecutive TSNs.
Okay.
So, and by using the iData extension, they don't have to. So, the small chunks, it's up to the stream scheduler. They can mix up all the chunks. They don't have to transfer the message at once in. What's not clear? Where can I?
No, I think it's clear. I get that you're offloading the function of the message data to the other sequence, fragment sequence number.
Yeah. You seem not to be convinced.
No. I'm just wondering, any other side effects that you're going to introduce with this, or?
No. The chunk header gets a bit larger, but
Okay, but that's not a concern here in this case.
no. We have to improve buffer management. This is a topic we really have to deal with because when you have, for example, a single stream and you fill up the buffer, and then now you come up with a small messages and say, well, this is very, very, very important that this message gets a high priority. And then you have to manage the buffer on the sender side and also on the receiver side, because when I send you a message, consists about 100 chunks, and I transfer 99 to you, and then I start with a high priority stream, and sending you messages with the high priority stream. You still have the 99 chunks, missing one. You can't deliver the message because you're missing one chunk for this message of the low priority stream. And now I start another stream with more higher priority. So you have two messages where you don't have all chunks you can deliver to the application, so your buffer blows up. This is one thing we have to investigate, how to solve possible problems.
Okay, great.
You mentioned something about an external interface that helps in testing.
Yeah.
Can you explain a little bit more on this?
The external interface.
Yes.
The external interface is, I think there's example code in OMNeT. It shows up as a real interface of the operation system, so you can use it like a normal network interface. It gets an IP address, and for example, we have run an SCTP client in OMNeT and routed the messages through the external interface to a real network where
Physical interface of the computer.
yeah. And there we have run an SCTP server, for example, and tested the interoperability of this model against the real implementation. And it's a good feeling when you leave the OMNeT simulation model and, well, we can talk to the real world. It's
Okay, good. Let's give him a final clap. Okay. So, very good first presentation. So our second speaker is